So by the name of that, you can understand that this is the reverse process of the Laplace transform. We're going to write down the formula. We're not going to use the definitions of inverse Laplace transform. It's going to be too complicated for us to do. We're just going to use the table of Laplace transform, inverse Laplace transform, to find the inverse Laplace transform of some common functions. Right. So that's the focus of this lecture. That is just to understand the inverse Laplace transform of function, then find Laplace transform of derivatives, because eventually what you want to do is to solve for the initial value problems using the Laplace transform. So the process, as I described in the last lecture, that is, so this is the process that you have differential equations. You're going to use Laplace transform to transform the differential equations to some algebraic equation, solve for the solutions, capital F of S, and then use inverse Laplace transform to find the solutions that you need in the time domain. So what is the inverse Laplace transform? Like if you have a Laplace transform of functions g of t, now the Laplace transform is denoted as capital G of S, then the inverse transform of g of S is defined as, again, the fancy L stands for Laplace transform, but if you put -1 here, that means the inverse Laplace transform of g of S is equal to g of t. So you transform, or you reverse transform the function in the frequency domain to the time domain. Now, some of the common functions that you will see when you encounter inverse Laplace transform or Laplace transform is that the inverse Laplace transform of 1 over s is going to be equal to 1. Right? You see an example where you find Laplace transform of 1 equal to 1 over s in the last lecture. Now, the inverse Laplace transform of 1 over s minus a is e to the at. Again, we have done the example, similar example like this in the last lecture. The inverse Laplace transform of n factorial over s to the power n plus 1 is going to be a power function t to the power n when n is equal to 1, 2, 3, so on and so forth. The inverse Laplace transform of k over s squared plus k squared. So we do something like that in the last lecture already. That's going to give you, this is going to give you psi of kt for the inverse Laplace transform. For the inverse Laplace transform of s over s squared plus k squared is going to be cosine of kt. Alright, so this is some of the common functions that you're going to see. And again, let me go back to the table, Laplace transform table. If you have the information in this column, then this is where you get the inverse Laplace transform. Again, if you have the information in this column, then in this column is the inverse Laplace transform. Let's do some calculations. In example 1, you have Laplace transform, inverse Laplace transform of 1 over s to the 5th power. And you're going to see if you can use one of the inverse Laplace transform in the table or not. So in this case, you have a table. You can go to, I can refer you to the table, or you can just use one of the formula here. So this is 1 over s to the 5th power, that is n plus 1. So n is equal to 4 in this case. So you can rewrite this inverse Laplace transform of 1 over s to the 5th power as follow. So this is inverse Laplace transform of s to the power of 4 plus 1. I just tried to mimic the formula that I got here. So what is missing? You are missing the term on the numerator. So it's not 1, it's the n factorial, for n is equal to 4 in this case. So you're missing the 4 factorial, so I'm going to put in 4 factorial. You don't have it, so you need to divide it by 4 factorial at the same time. So you multiply with 1 over 4 factorial. You follow this calculation? Right. Or there's another way to present this problem. That is, so you're missing 4 factorial. You multiply by 4 factorial, but at the same time divide it by 4 factorial. Something like that. Okay. And then you can pull 1 over 4 factorial out of the inverse Laplace transform operations to get inverse Laplace transform of 4 factorial over s to the power of 4 plus 1 times 1 over 4 factorial. For this inverse Laplace transform right here, this is t to the power n. For n is equal to 4, so t to the power of 4 times 1 over 4 factorial. And 4 factorial is equal to 24. So 4 factorial is what? Is 4 times 3 times 2 times 1. Therefore, this is equal to 1 over this is equal to 24. So this you get 1 over 24 times t to the 4th power. Okay. Now for the second example, you have inverse Laplace transform of 1 over s squared plus 4. So s squared plus 4 or s squared plus 2 squared. Okay. So in the denominator, you have s squared plus 2 squared here, you have s squared plus 2 squared here. But for this inverse Laplace transform, you need s on the numerator. So in this case, s is the variable, so let's not do that, right? But what you can do is that you can multiply and divide it by a constant k. Okay. So 1 over s squared plus 4, or 1 over s squared plus 2 squared, the missing part on the numerator is 2. So you can multiply and divide it by 2. So this inverse Laplace transform is 1 over s squared plus 2 squared. So you're missing a 2 on the numerator. You multiply that by 2 and divide that by 2 as well. Then you can pull the 1/2 out of the inverse Laplace transform operations. Inverse Laplace transform of 2 over s squared plus 2 squared times 1/2. And this inverse Laplace transform is psi function, so psi of 2t in this case. This is equal to psi of 2t times 1/2, or you can write this as 1/2 times psi of 2t. So that's the inverse Laplace transform of some common functions. Alright, so when you do these calculations, you see that I have some move that I use. That is, you pull out the constants, or you pull the constant out of the inverse Laplace transform operations. You are allowed to do that because inverse Laplace transform is also a linear operator. That is, inverse Laplace transform of linear combinations is linear combinations of inverse Laplace transform. Okay, and that is the theorem I want to give you. So the inverse Laplace transform is also a linear transform. That is, for constants alpha and beta, the inverse Laplace transform of alpha times capital F of s plus beta times capital G of s is equal to alpha times inverse Laplace transform of capital F of s plus beta times inverse Laplace transform of G of s. Okay. Where, again, alpha and beta are constants, and capital F of s and G of s are the transform. Of some functions, f and g, little f and g. So again, inverse Laplace transform is a linear operator. And that's what you can do now. Is in example 2, in example 3, I want to find the inverse Laplace transform of this fractions. So there's no straightforward answer for this inverse Laplace transform functions. You cannot refer to the table. There's no exact or similar fraction like this. But what you can do is you can use the linear operations properties of inverse Laplace transform to separate these fractions into 2 different inverse Laplace transform. So first thing first, what you can do is the inverse Laplace transform of negative 2s over s squared plus 4 plus 6 over s squared plus 4. And you can turn this into 2 inverse Laplace transforms. So inverse Laplace transform, or 2 times inverse Laplace transform of s over s squared plus 4 plus 6 times inverse Laplace transform of 1 over s squared plus 4. So inverse Laplace transform of s over s squared plus 4, again, you can go back to the Laplace transform table, or you can use one of the formula that you see earlier here. Okay, but let me go to Laplace transform table just to show you how that can be done. So you have inverse Laplace transform of s over s squared plus 4, or s squared plus 2 squared. Right, so when you look at this formula right here, the function you get is s over s squared plus 4, or s over s squared plus 2 squared. So in this case, b is equal to 2. So the function you got is s over s squared plus 2 squared. Therefore, the inverse Laplace transform of this function is cosine of 2t. Okay, let me go back to the note here. So for this one, this is cosine of 2t. So the first term give me 2 times cosine of 2t. Now for the second inverse Laplace transform, you have inverse Laplace transform of 1 over s squared plus 4. So let me go to the Laplace transform table. Get rid of this. So the one that we're looking at is this formula right here. Right. So you have 1 over s squared plus 4. So 1 over s squared plus 4. Or instead of 4, you have 2 squared. Right. So what is missing on the numerator is missing b, or 2 in this case. So what you do is you multiply and divide it by 2. So 2 here multiplied by 1/2. Okay. And the inverse Laplace transform of 2 over s squared plus 2 squared give you sine of 2t. All right, so very similar to the last example that we did. So let me go back to the notes here. So this one is 6 times inverse Laplace transform of 2 over s squared plus 2 squared times 1/2. And then you can pull out the 1/2, or you can pull 1/2 out of the inverse Laplace transform operations. You got, this is 2 cosine of 2t plus 6 over 2 times inverse Laplace transform of 2 over s squared plus 2 squared. And this inverse Laplace transform gives you sine of 2t. So this is 2 times cosine of 2t plus 3 times sine of 2t. Okay. So this example just to illustrate the idea of linear operator on the inverse Laplace transform. Okay. Now I'm going to give you another example, example 4, on finding the inverse Laplace transform of this functions, s minus 1 over s plus 1 times s minus 2. And you're going to encounter a lot of this in our calculations later when you take a look at applying Laplace transform in solving the initial value problem. So this is just foreshadowing. I want to find the inverse Laplace transform of this particular fraction. Okay, so how would you do that? You cannot immediately separate these fractions into 2 different fractions. But what you can do is that you can solve for this, or you can separate this fraction using partial fraction decompositions, okay, which is a technique that you learn in calculus 2. So for partial fraction decompositions, especially for this problem, you have the factor in the denominator, right? You have 2 factors, s plus 1 and s minus 2, and the 2 factors are linear. So because the 2 factors are linear, this is what you can do. So you take out the fractions, s minus 1 over s plus 1 times s minus 2. So because the 2 fractions are linear, you can do a over s plus 1 plus b over s minus 2. So the factor on, or the constant on the numerator is, the factor on the numerator is 1 less than the factor in the denominator. So in this case, you only have s, right? S to the first power, then the 1 on the numerator is s less than that, right? So s to the 0. That's why you don't see s on the numerator. If you have later on when we deal with quadratic term, right? So you have s squared, then the factor on the numerator should be a times s, something like that. Right. So now, because again the factor in the denominator is only the first to the first power, so that's why you have a over s plus 1 plus b over s minus 2. The next step is to combine the 2 fractions on the right hand side. So you have s minus 1 divided by s plus 1 times s minus 2. You combine the 2 fractions, you have a times s plus minus 2 plus b times s plus 1. So you find the common denominator, and the common denominator is s plus 1 times s minus 2. Now at this point, the denominator are the same, they are different from 0, you can get rid of it and you just match the numerator on both sides of the equation. That is s minus 1 equal to a times s minus 2 plus b times s plus 1. And the job is to find value of capital A and capital B. And there's multiple ways to do it, but usually my go-to method is just to get rid of one fraction, just to get rid of one constant and find the value of the other constant. So if s equal to 2, then you have 2 minus 1 equal to a times 2 minus 2, so this is 0, plus b times 2 plus 1, so here you have b is equal to 1/3. Okay. And when, or if s equal to negative 1, so you have negative 1 minus 1 give you a equal to a times negative 1 minus 2 plus b times negative 1 plus 1. So this is 0, therefore this gives you a to be negative 2 over negative 3, or positive 2 over 3. Okay. So you have the value of a, you have the value of b, you can put it back to the partial fraction decomposition. So let me quickly note that this is partial fraction decompositions. So the inverse Laplace transform of s minus 1 over s plus 1 times s minus 2 is now equal to the inverse Laplace transform of 2 over 3 times 1 over s plus 1 plus 1 over 3 times 1 over s minus 2. So inverse Laplace transform of a sum is the sum of inverse Laplace transform. So you can rewrite this as inverse Laplace transform of 2 over 3 times 1 over s plus 1. Or you can pull out, a 2 over 3 as well. So 2 over 3 times inverse Laplace transform of 1 over s plus 1 plus 1 over 3 times inverse Laplace transform of 1 over s minus 2. Okay. Now you have two inverse Laplace transforms that you need to find. I'm not going to use definitions, of course. We go into Laplace transform table. So you have one to be inverse Laplace transform of 1 over s plus 1. So 1 over s plus 1. Let's take a look at this example, or this formula. You have 1 over s plus 1. What I'm trying to do is I try to mimic this formula. The formula is 1 over s minus a. So you need to have the negative, right? Or the subtractions on the denominator. So I turn this into 1 over s minus negative 1. Therefore, the inverse Laplace transform of this function is e to the negative 1 times t, because a in this case is negative 1. So let me do that. The note here, this gives me 2/3 times e to the negative 1 times t, which is e to the negative t, plus 1/3 times e to the times the inverse Laplace transform of 1 over s minus 2. So 1 over s minus 2, get rid of this function, so 1 over s minus 2. Right. So you already have the subtractions in the denominator. You have s, and a is going to be equal to 2 in this case. Therefore, the inverse Laplace transform of 1 over s minus 2 is e to the 2t. This is 1/3 times e to the 2t. So that's how you find the inverse Laplace transform of some functions. So in this 2 example, I want to illustrate the idea of the linear operator properties on inverse Laplace transform, and also show you how to read the Laplace transform table to convert inverse Laplace transform of some functions to another function in the time domain. So when you do something like this, more often you will encounter the idea of partial fraction decompositions. So in example 4, we have some very basic partial fraction decompositions where the factor in the denominator is going to be linear factor, right? Linear because it's just to the first power. Definitely, on the cases when you encounter the factor in the denominator to be not linear, so this is linear to a certain power, or this is a quadratic factor, or the quadratic factor to a certain power. We're going to see a linear factor to a certain power, or the quadratic factor. We're not going to see the quadratic factor to a certain power because it's very complicated. It gets complicated very quickly. So therefore, when you see example in this lecture, the focus is only on the linear factor to a certain power, and a quadratic factor.